Hello? Okay. So our guest today is Dr. Stephen Chu. He's Director of Lawrence Berkeley National Labs and Professor of Physics and Professor of Molecular and Cellular Biology at UC Berkeley. He has a long and distinguished career working in physics research, including work on the cooling and trapping of atoms using laser light, for which he shared the Nobel Prize in Physics in 1997. So please join me in welcoming him. He's going to talk about the energy problem and what we can do about it.
Thank you. I know you all know that I'm not Larry Page, but I just have to share a little joke. I just gave a talk at the AAAS meeting in San Francisco, and Larry Page and I were the two keynote speakers, and Larry wanted to switch places. So just to tell the audience, he was supposed to talk on Saturday, I was supposed to talk on Friday. He wanted to switch places with me. So I just wanted to tell the audience that I wasn't Larry Page, that this is what Larry looked like. And you can find by Googling Larry, you get 32,000 images of Larry in a tenth of a second. But couldn't resisting, I wanted to compare myself to Larry, so I Googled myself. And so I get 1/50th the number of hits, more than 1/10,000th the number of dollars. But the reason is, why was I there? So Larry had written me an email and said, I want to switch places with you. You're no keynote at AAAS. I'm speaking on Saturday, and you're on Friday night. And he wants to swap. So I said, well, I didn't really want to swap for several reasons, because I had a group meeting at Stanford on Saturday. So I gently said, dear Larry, thanks for he gave my wife and I a ride to Davos and back. And according to UC rules, I have to write them a check for the cost of 2 coach fare tickets so it could fly on Google Air. As for the requests, while I'm willing to switch, this is a gentle hint. There would be a lot of people who are arranging their schedules to hear you that would be greatly disappointed to get me. And he didn't get the hint. So he writes back, if it's all the same to you, I would love to switch. I'm sure people would be better off seeing you than me. And so, yes, this sounds like Larry, you're saying yourself. And I'll get all the smart people who want to go to your talk. Thanks. So I said, okay, Larry, if the AAAS guys can do it, then it's okay with me. This is like 2 weeks before the thing, and the keynotes draw 3,000 or 4,000 people, and it's all printed up. So then John Holgren, who's the president of the AAAS, actually was very good. So I checked overnight for those in the AAAS management who might consider to have their oxen have been gored. And my position is that we should do whatever is necessary to pull up the switch without dissent or fulmination. Very poetic. But I think there were some people angry at me, and so this is really to deflect the anger to Larry. So with that, let me talk about something that I have become not only very interested in, but also very concerned about, and that's the energy problem. And so this is a bad news and a good news. I want to spend most of the time talking about the good news, because the recent documentary Oscar Award winner talked a lot about the bad news. This is Al Gore's movie. But I think the energy hits in many sectors. It's intimately tied to national and international security, economic prosperity, and of course, the environment, particularly climate change. Just one little tidbit that you might not be familiar with. The United States spent $250 billion importing fossil fuel in 2005. In terms of the federal budget, this is in other big numbers like the deficit, that's $750 billion. In terms of the federal budget, there's only a couple of things that exceed a couple of $100 billion. That's health and human services, Social Security, Medicaid, defense. I think there's not much else. There's 3 or 4 things, and then after that, this is number 4 or 5. So this is a huge amount of money, and in the long term, it will increase even more, because we're importing roughly 60% of our oil, and we're increasingly importing more and more natural gas. So it's some economic consequence. I do very, very briefly, what is the evidence that the climate change is caused by people? Now, the IPCC report says the probability is between 90 and 99% that the climate change we're seeing is caused by humans. So where does that come from? So this is a sampling. The red is the actual measurement of temperature, and the hash is a climate model where you fold in volcanoes, which change how much sunlight is absorbed if you stick this particulate matter and sulfur dioxide in the air. Natural causes, solar variations, anything that we didn't cause, you stick into the current models, and you find this gray hash that doesn't seem to follow the red line, which is the measurement of the worldwide average. But if you stick in what we know to have been caused by humans since the Industrial Revolution, because the amount of CO2 kind of goes like that and shooting up, the amount of nitrous oxide, methane, caused by the Industrial Revolution, then you start to get a reasonable fit. So this is suggestive that perhaps it's caused by humans. And then there are correlations that we're beginning to notice. This is a correlation between, in the Atlantic Ocean, the severity of hurricanes in the Atlantic and the temperature of the water in the Atlantic. It's not just a correlation, because below a certain temperature of ocean surface temperature, you won't get a hurricane. And so we understand a little bit of the physics of what actually feeds these hurricanes. But this correlation is, I would say, 70% probable that the correlation is real. It's not 99%, because you can imagine putting up hog future prices and other things that might not be directly correlated with hurricanes, and you could get some similar things, because if you notice, it's only this last little tidbit that's indicative of something. Okay, so again, suggestive, not proof. And so the great concern that I've had over the last 4 or 5 years is really what's going to be happening to our predictions of climate change. And so I have to remind you of something the greatest American philosopher of the 20th century said about this. That's Yogi Berra. And he said many wise things, but he said in this particular case, predictions are hard to make, especially about the future. And so the prediction you just saw of climate change over the last 150 years is predicting the past. And as we go forward, we need to get more and more refinements on what happened in the past, because that is a good warm-up to predicting the future. But there are predictions. There are predictions of increased damage due to floods and storms, population displacement, a combination of the sea level rise and the increased severity of storms. It's not just the slow sea level rise that we're afraid of. It's that combination. And so one can imagine if Louisiana, and particularly New Orleans, gets hit with another Category 4 hurricane in the next 5 years, well, there will be serious questions about whether you want to rebuild, given those predictions. There's all sorts of things, increased species extinction, diseases that depend on temperature and moisture, things like malaria, dengue fever, and other things. The malaria especially is predicted to rise. The deaths due to malaria are predicted to rise due to climate change, because a lot of towns, villages, whatever, are trying to stay just out of the mosquito belt. So these are all sorts of things. But I want to talk about one prediction that hasn't actually gotten that much discussion yet, but it's increasing. And that is water shortage. So this is a paper taken from the Proceedings of the National Academy of Sciences, 2004. And it takes 2 climate models. B1 is a very unalarmist climate model. You have aggressive control of carbon dioxide emissions. You reduce them, and you see what's going to happen. A1 is a business as usual, which means a 1% increase in energy efficiency per GDP, but no real attempt to control carbon dioxide emission. Okay? And so this is what's predicted to occur in California in this century. In the one of the least alarmist models, 30 to 70% decrease in the snowpack, 50 to 75% decrease in alpine subalpine forests. So these two are a major part of our water source. As you know, it rains beginning around October to mid-March, and then after that, it doesn't really rain much, if at all. And so the snowpack and the moisture captured in the forest and the snowpack is a major part of the water storage. It's not just the dams. And it's that slow delivery of water over the next several months that helps us with our water supply. For those of you who remember droughts where the decrease in snowpack was 20 or 30% for 2 years in a row, I had some nieces and nephews that were little toddlers that were told not to flush toilets, even number 2, and for 2 years, and they had to break them of that habit several years later. That's a trivial thing. I don't know what it will be like if we're missing 50% of our snowpack on a continuous basis. And that's the mid-range of the least alarmist model, or one of the least alarmist models. And the more alarmist means that you have to migrate from California. Or at the very least, you secede from the Los Angeles area, which usually brings applause in Northern California. This is not only true in California, this is also true worldwide. This is the average glacial thickness change per year. So now it's roughly of scale a meter. Decrease per year worldwide. And as you see, it's accelerating. This is the solid lines, the integrated decrease in snow. Particularly worrisome is the Tibetan snow and glacial range, if you will. And it supplies 10 of the largest river basins. Roughly half the world's population gets some of its water from these river basins. So this includes most of Pakistan, the Ganges, and all the river basins in India, the Yellow River, the Yangtze River in China. All supplied by the steady melting of glaciers and snow in the Himalayas. And so this is actually more than a meter per year now of melt. The Yellow River in northern China is now sometimes running dry in the summer. And China is now thinking of shipping water north via aqueducts. But the whole water supply system, again, is threatened because it's the slow, steady melt that is a lot of the water storage. This has not gotten that.
In the audience now, so we have Larry Page in the audience now, so we can do a comparison between these two.
No, he's coming. So Larry, you missed all the jokes about you. So anyway, so these are some of the issues that I think, in fact, the water storage and the water supply problem is, I'm guessing, one of the things that will hit home earliest in terms of the economic and social impact. But we'll see. Again, it's a prediction. There's another thing you should know about if you don't already know about it. Suppose this is the CO2 emission, and suppose in the next couple of decades we actually get hold of it and then greatly decrease it. What will happen? We sequester that CO2 from natural causes, from natural processes. And the answer is we don't really know. This is one prediction. So what happens is this burp of CO2 sits there and it continues to integrate, and then you see this slightly gentle decrease. This is due to natural sequestration processes in the land and the ocean that eventually lead to mineralization of the carbon, or long-term sequestration, either in some tundra or, quite frankly, in fossil fuel deposits like coal. The debate is whether this natural process is a few hundred years, time constant, or a few thousand years. It's not going to happen in 20 years or 50 years. Okay, so that's the debate. So what we do today and for this century could have lasting impact unless we figure out some very clever way of economically sucking the CO2 out of the atmosphere as well. So it's something to think about. So as this CO2 is up there and slowly beginning to be sequestered, the temperature will continue to rise. The reason the temperature is still rising is because there's a lot of deep ocean mixing, and the ocean is a huge capacitor. And in fact, the general feeling, the consensus among the climate modelers is that we have about 0.6, 0.7 degrees centigrade today, even if CO2 emissions drop to 0 tomorrow. So then there's still a glide upward. So those are things we should be concerned about. So I think the dual strategy is we've got to maximize energy efficiency, use it in a smarter, cleverer way, and not waste it, and of course develop new sources of energy. California has, over the last 30 or so years, been essentially flat in its electricity consumption per person. The rest of the United States, if you take away California, which is 11 or so % of the population, has gone up by 60%. And so, and then California is now wanting to drop this down, but in any case, there is an example, an existence proof that the economy doesn't really have to be killed if you use energy more efficiently. There's an inflection point here. There was a high energy physicist at Lawrence Berkeley Lab and also UC Berkeley, Art Rosenfeld, who is Enrico Fermi's last student, a very distinguished high energy physicist. In the first oil crisis in the 70s, he said he just completely left physics and said, what can I do to help with the energy problem? And he decided the best thing he could do was to help in energy efficiency. And a lot of ideas flowed out of Art, grabbed by others. This is one thing that Art did personally. He went into an appliance store and noticed that refrigerators could vary by factors of 2 and 4 in energy efficiency for the same size refrigerator and the same cost. So you don't have to be a refrigerator expert to realize that the first factor of 2 is for free. And so what he did is he then convinced California to put in increasing refrigerator standards of efficiency. First, labeling, voluntary labeling, Energy Star efficiency type of labeling, but then increasing standards. So this blue line is the energy consumption of refrigerators. It's gone down by a factor of roughly 4.5 since the middle 70s. Meanwhile, the size of refrigerators has gone up from an average size of 18 cubic feet to 22 cubic feet. It's asymptotically approaching what you can get inside of a standard kitchen door. And the cost of the inflation-adjusted cost of refrigerators, initially when the manufacturers were faced with this, they said, no, 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 this is going to be terrible. The cost of refrigerators is going to double all this other stuff. And what happened was it actually went down by more than a factor of 2. Now, one of the surprising things is why did the efficiency increase a couple of years before the standard? It's because industry was warned the standard was coming. So after they stopped trying to fight it, they started thinking. This is also true of the Clean Air Act for sulfur dioxide and nitrous oxide emissions. After they stopped trying to fight it for a decade or two, they started thinking the cost was a very, very small fraction of what they said it was, and the electricity bills went, I think, I'm not sure, but I'm guessing, within 5 or 10% of the same. So we see this over and over again. If we ever want to get a carbon cap and trade or cost on this, give them some time and then give them a 15-year ramp up. But you just got to get rid of the loopholes.
Was the cost of, say, the Clean Air Act, the actual technology, more or less than the cost of the lawyers and lobbyists that would deploy?
Oh, the lawyers are always more money, without a doubt. Okay, and in the long run, it's not only that the full cost, if you include all the health costs, the cost of agriculture and forests and fisheries, the acid rain issues, actually the acid rain also rots out the infrastructure, bridges, buildings, roads much faster. If you fold in all those costs, it's like 1/10 or more. It's not even close. And the same is, except with climate change, it's in a totally different scale and a totally different cost. But it's a similar thing. So now, what about refrigerators? Is this a big deal or not? Well, this bar over here is what the electricity consumption would have been had we stayed with 1974 efficiency, the average efficiency. And this is what we're using today. So this is the amount of electricity saved even though we went from 18 to 22 cubic feet. So it's not a diminution in lifestyle. I just want to emphasize this. This is often confused. This is all the electricity due to hydro in the United States. This is nuclear, 20% of electricity generation in the United States. Just refrigerators is some reasonable fraction, a couple percent, 3% of all electricity. There were less spectacular gains, but equally important gains in heating systems and HVAC, okay, of scale 50%, 60%. So efficiency is really big. I want to emphasize that this is how we consume energy in the United States. These two down here are what we spend in energy in commercial buildings and residential buildings. In commercial buildings, 75% of this energy is electricity. It's not heat. Transportation, which gets a lot of coverage, is about 27% of the total energy needed in the United States. So there's a lot more wasted here than here, actually.
These are cumulative stacks?
This is how much energy per year that we are. This is the distribution of, you know.
Transportation is more than residential, or that's the
Transportation. This is all of transportation: trucks, trains, cars, airplanes, and. Oh no. Oh, no. These are separate lines. I understand the question now. It's not cumulative. Okay. And things like compact fluorescent light bulbs, due to electronic ballast, so that the energy oscillates between the plasma and the light bulb, and it used to be a magnetic field and a thing that was actually suggested by Art Rosenfeld, and that was developed at Berkeley Lab, and this is beginning to transform lighting in the United States, because you can get, this is 4 or 5 times less energy than an incandescent, and the phosphors now look like daylight. A lot of people don't like daylight. They like that red-orange glow. That's fine. You can actually make them for a little bit more money. You can get the red-orange glow of incandescent and slowly wean yourself to daylight. So this is what's been happening. This is a time-lapse picture of energy consumption in the United States, relatively flat, in part due to, as a function of GDP. So this is yearly changes, plotted as GDP per person, per capita, and primary energy use per person in this very funny unit, billion joules of energy per year. And so we're the price leader. We're the richest, and we use the most energy. And other countries are catching up. The European countries are roughly a factor of 2 less than us, but Australia, Canada are shooting up. And then the real question is, what's going to happen in India and China, where there are 1.3 and 1.1 billion people, respectively. So we're about 25% of CO2 emissions in the world, with 600 million out of, and the denominator is 6.5 billion. But let me tell you about this, the units. Because gigajoules per year is not a unit that you're really used to. And in fact, physicists don't really know what that means. So I decided to convert it into something that we all understand. Now, before the Industrial Revolution, the person's wealth is really defined by how many servants or slaves they had working for them, right? Usually it's none. And so that's a baseline. But if you got 50 servants, you're pretty wealthy. And you can also throw in the amount of cows and horses and other things. So, so let's convert it to that wealth. And so, well, what's a person consume? Well, a person consumes roughly 2,500 calories per day. 2,000 to sustain life, 3,000 if you're a real athlete type. And, but just takes a middle ground. And so this corresponds to 1,000 energy servants per person in the United States. That's why we enjoy a good standard of living. We have 1,000 people working for us. The average person in China only has 100. Okay, now the rest of the world wants to get to 1,000, let's say. And is this actually possible? So I did a little calculation. Now, the peak population in the world is now predicted to be something on the order of 10 billion people. This is incredibly good news. Within this century and maybe slightly into the next century, the population will peak and then start to decline, not folding in some gross calamity, just natural stuff is happening. What's the natural stuff? Well, I don't really know, but it's been observed that when societies, or within a particular society, when people get richer, they have fewer kids. My personal theory is that it's because of late night TV, but that's speculative. But it cuts across all cultures, all subsegments in the United States, if you will, and in the rest of the world. And so Europe, for example, has negative growth, and many countries in Europe are giving tax incentives to have more kids. And it's the developing countries that have lots of kids. But as the economic wealth continues to climb, it is now predicted, and this number actually goes down with each succeeding estimate. So let's say we consume 10 to 12 kilowatts per person. Europe contains 5 or 6. But suppose we get the equivalent of 3 or 4 kilowatts in current energy. That's not to say we should be huddling around in sweaters and things. It's either getting more efficient or getting energy sources that are less CO2 emitting, and either one will do this, okay? So this is 0.04% of the Earth's solar power hitting the Earth, in order to give everybody the same standard of living that, let's say, the middle class enjoys in Europe. Yes?
Is that the power that actually reaches the surface?
Yeah, yeah. Well, within a, that, I'm not going to quibble 30%. It doesn't really matter. Okay, but because you can quibble about whether you want 400 energy servant or 1,000 or 10,000. And so the idea here is, can the U.S. get down to here, and Europe and Japan and others want to get down to here. You notice France is already almost down to there, because it's about 78% nuclear. Okay, so this is not really kind of crazy, but what we're really afraid of is China is going to follow in the United States' footsteps, and then they're going to decide when they get about here that, oh my gosh, we should be down here for a lot of reasons, like economic prosperity, because you want to consume energy in a very efficient way, whereas it's going to take a lot more work for the United States to get down to here, because we have an infrastructure, a city, suburban sort of thing that's a little bit different. So this is known in economic circles as the Kuznets curve. This is time, advancing society, maturity, whatever. This is anything you want it to be, from number of kids per family to mercury pollution to CO2 emissions to anything you want. And the fundamental idea is you're up, you're here, you're going higher and higher, and you're saying, oh my gosh, the Industrial Revolution is killing people right, left, and center, as it was in the late 19th century in England and the US, and then you start to clean up the air. And so the question is, can China and India be coaxed to leapfrog past these mistakes and go to here? And that's the $64 question. If they don't, we're in deep doo-doo. But it's to their advantage, so that's the good news. So when I got to Lawrence Berkeley Lab 2.5 years ago, one of the reasons why I took the job is this, well, if we can get some of our very best scientists, and it's a pretty good lab. Of those of you who don't know Lawrence Berkeley Lab, it's just on a site overlooking University of California, Berkeley. It's a national lab. It has a budget of about a little over $500 million a year. In its history, it's had 11 Nobel laureates, but better than that is 9 of them actually did their work at the lab, as opposed to me. And opposed to some of the Ivies who get the Nobel laureates after they've done their Nobel laureate. In fact, there's a couple of them who did their Nobel Prize work before they were made faculty members. And then they said, maybe we should make this guy a professor. It's happened a couple of times, and a whole bunch of National Academy members that route. And right now it has 3% of the membership of the National Academy of Sciences at the lab. So we're thinking, is it possible to capture solar energy and convert it into more useful forms of energy? The most valuable form of energy by far is transportation fuel for this variety of issues having to do with energy independence. It's the most costly form of energy, all sorts of things. And because of that, you don't have to be as good in order to get economic value. You can also perhaps create a new generation of photovoltaic cells into electricity. Once you have electricity, there is an energy storage problem of how you can store it and then convert it back to electricity on demand in an economical way, or whether you can convert electricity in a much more economical way to first split water, make hydrogen, and then possibly to go further to make methane. Methane is good because once you get methane, it's a good feedstock for a whole bunch of things, from fertilizer to plastics to everything. Or you can, and you can store it more easily than we can hydrogen, and we have a distribution system, natural gas pipelines, and so then off you go. So these are a variety of ways. In the long run, one wonders whether you can make artificial photosynthetic systems that would ultimately be better than nature. Now, that is something that, while I have a lot of respect for nature and these couple billion years of engineering, design, testing, redesign, in the end, you're not as constrained as nature is. And the simple example I have is that when people first wanted to learn to fly, they started to try to imitate large gliding birds. They would strap wings to their arms, they would jump off a cliff and hope for the best. And even the Wright brothers' first plane, the way it actually controlled its flight was due to wing warping, not flaps, because it was a lesson learned from birds, although the propulsion had nothing to do with a bird, this propeller. And in the end, the 747s actually do work better than Eagles in terms of transporting people, because they're no longer constrained by materials and everything else. But to be fair, 747s don't reproduce. But anyway, they are better for what we wanted them for. And maybe we can develop a photosynthetic. What is photosynthesis? It's capturing sunlight and making chemical energy. And can we do it better? Okay, some targets for solar. I think there's roughly a factor 3 you need before most of the people, not the more environmentally conscious people, but most people will think of slapping it on the rooftop, or where you would, by its very nature, stick it on the rooftop of a building, because it's economical to do that. But you need about a factor of 10, I think, before it's wide-scale deployment. Why this factor of 3? It's because right now you can sell electricity back to the power companies at retail costs until your electricity bill is 0. But that's about a factor of 2.5 less than it costs to generate the electricity. So that is that's an underlying subsidy that you're asking the power companies to buy back at retail. And what it costs to generate at wholesale is very different, because they don't have all the other stuff, the accountants, the lawyers, the power lines, probably in that order. Well, no, the lawyers first, then the power. So that's the other issue. This is a huge gain if we can get some solar, and photovoltaic or solar thermal, doesn't really matter. And it's not clear what's going to win. But in any case, this is how much of the desert land you would need where there's a lot of cheap desert land, and this is the fraction you would need to supply the current electricity needs of the world at 20% efficiency. Okay, so there's a lot of energy hanging around. It's just a matter of money and cost. We are thinking of, because we're good at nanotechnology at the lab and at Berkeley, and so this is an ideal. Let me just walk you through it. You have sunlight, it absorbs it and creates electrons in holes, and 1 nanoparticle can do the absorption and the creation of the energy. In this particular scale, this is of scale 100 nanometers. Why 100 nanometers? Because you can make nanoparticles like cadmium selenium nanorods that are essentially perfect at that scale. And in this case, the electrons in the holes are differentiated by a conducting polymer and a semiconductor nanorod, where you can maybe we know how to grow these nanorods, and can we slap electrodes on them of the scale? And the real trick here is, can you make multiple interfaces with no losses here? And if you can do that, you've got something that's amenable to wet chemistry and real-to-real process. And so right now, these things are not aligned. These things, where you do separate a nanoparticle to absorb the sunlight and another one to conduct away, but since they're not aligned, there's lots of losses. They're only 3 or 4 or 5% efficient. You really need to get up to 15 or 20%, but the other part of it's good. It's cheap stuff, and it's real-to-real process. And that's what you would really need to get cheap. Not batch stuff, batch wafer stuff, but really real-to-real, like printing newspaper. Another area that we're focusing on is, can you create bioenergy? And so recently it's been announced that BP has selected the University of California, Berkeley Lab, and University of Illinois to develop an Energy Biosciences Institute. The idea here is that you would have some plant that would convert the basic ingredients of sunlight, CO2, water, and nutrients into biomass, and that these plants can be much improved so that they could use much more efficiently water, sunlight, nutrients. They could be drought resistant so that you don't have to use irrigation, and pest resistant. And then the conversion of biomass into chemical energy. And this is where the economical gain is. Right now, it costs about 2 to 2.5 times more to convert cellulose into ethanol than it does to convert sugars or starches into ethanol. The basic idea is that sugars or starches, it's easy to break them down into simple sugars, and then you let this 5,000-year-old process, namely fermentation, do the rest of the work. And in order to break down the cellulose, it takes a lot more energy, it takes a lot more money, mostly in the cost of enzymes. The average production of agriculture in the world and the United States has grown dramatically. This is, corn is, by the way, I'm not showing this because I think corn is the right solution. It's definitely the wrong solution. But I'm just showing this to let you know that breeding of corn in this century has led to an 8-fold increase in productivity per acre. And in the world, about a 2.5-fold increase in agricultural productivity per acre, where a lot of the world isn't using modern agriculture yet. Okay? So there's potential. That's the world. This is the population from 1950 to 2000. And this is what would have been planted, but this is what actually was planted because of modern agriculture. So what is a better plant? Well, they would be grasses. These are grasses. This is switchgrass, but the actual choice in the Midwest would probably be a plant called miscanthus. This is a midget standing next to a field of grass. No, she's about, actually, in truth, these are foot markers, and she's not that tall. She's about 5'3". She's a graduate student of Stephen Long, a professor there, who has taken this grass from a botanical garden in Chicago and grown it on unirrigated, unfertilized land. It's a perennial, which means you plant it, and then at harvest time you chop off the top, and since it's a weed, next year it grows with the same vengeance, but you didn't get the roots. And because they're perennials, you can actually get these guys to think of getting into develop symbiotic relationships with bacteria, so they fix a lot of their own nitrogen. Actually, sugarcane fixes a lot of its nitrogen. It, too, is a perennial. So this is an estimate. If you had 50 million acres, okay, what is that? Where I get that number from? That's a lot of land, you say, in the United States. That's the amount. We have 58 million acres officially listed as USDA as surplus land, which we pay farmers not to plant, in either long-range conservation plots or year by year. Okay, so this is excess land. Okay, and the estimate of using this stuff is half to all of current U.S. consumption of gasoline. The plant on the right is remarkable. It's 2% efficient. Per growing season, for all the sunlight that hits the ground, it shows up as biomass above the roots. Overall, it's about 7% efficient if you consider everything that it's generating. But let's say 2%. This is an unimproved crop, or an unimproved weed, if you will. Okay. Here's an example of some improvements. The Joint Genome Institute, which is run by Berkeley Lab and Livermore, and in partnership with these other institutions and led actually by a scientist at Oak Ridge, we have sequenced the poplar tree. It's a very fast-growing tree. It's got 45,000 genes, roughly twice the number of genes of you. So just think about that. It just means that poplar tree is more complex, I guess. And this is a modification of the transcription factors in this tree. So under the same growing conditions, it has twice the amount of usable biomass, the woody stuff, as the wild type. And this is just the beginning. And there actually, you can think of all sorts of things of using modern biological methods to promote long-term carbon sequestration and all these other things, okay? So it's actually, the gene regulation was actually related to human steroids. So you can say that this is a plant on steroids. Okay, so what's the deal? Why isn't this commercially done today at large scale? So here's a picture of a pine board or any cellulosic material. This is the stuff in the cell walls. And if you magnify this, what you find are these cellulose microfibrils, which if you magnify at the molecular scale, what you ultimately see are simple sugars, 5-ring or 6-ring sugars strung together in a long polymer. But that's not all. In addition to the 6-ring and 5-ring sugars, the cellulose and hemicellulose, and this is the average breakdown in this weed miscanthus, is a stuff called lignin. And the lignin is a very complex set of molecules of multiple rings that were designed by a plant to actually protect the plant and the cell wall from attack by microbes, fungi, bacteria, anything like that. So it's a self-defense mechanism. And it's this lignin that actually prevents us from efficiently taking all the chemical energy of this plant and converting it efficiently into ethanol. And so this is a pilot plant of a commercial ethanol production from cellulose, and it starts either by steam explosion or hot acid, that this stuff tries to separate the lignin from the sugars. After that, you have to get rid of the, let's say, the hot acid, and then you sprinkle a set of enzymes that take the long polymers of these sugars and break them up into simple sugars. The biggest cost are the cost of the enzymes currently. The second biggest cost is the energy invested in order to break this stuff down.
How much more efficient is this kind of process than a gasification process that doesn't try to do it?
The verdict ultimately, the verdict is not in, actually. One wants to look at taking the biomass, drying it, and turning it to syngas. And so I can't really say, but there's just the beginning of this stuff. Let me go back to the most valuable form of energy is the liquid fuel. And so the syngas requires another step. If you're going to take the syngas, pass it over steam, turn it into hydrogen plus water, and burn it to make electricity, there's not enough money in that yet.
I'm interested in biological material all the way through a liquid fuel through a syngas process versus through to dry alcohol through one of these processes.
I think that this is the syngas route into methanogens, into biofuels is still more expensive. I mean, okay, but this is another thing that we're going to be looking at, okay, and other people are going to be looking at. Okay, so the biggest cost is the enzymes. So can we get better enzymes? In fact, right now what they do is they take microbes and they grow them, and then they recover the enzymes from the microbes and sprinkle it on the cellulose and hemicellulose. And Novozyme and Genicor are the primary companies that do this. But as I said, the price has gone down by an order of magnitude, but it needs to go down by another factor of 2 or 3 in order to get production costs the same as production from sugar cane. So here's a critter who has some of the right enzymes. This is a termite. This is a multi-billion-dollar industry to keep them from eating your house. But inside the termite, this is the gut, or there's a multiple gut of a termite, there live up to 100 microbes that actually break down the woody material into a chemical fuel that the termite could use. And so the relationship is that the bacterial colonies actually have a little carrying charge, and they get a little bit of the energy. They pass the rest on to the termite with the instructions, go get me more wood. You can extract this. So we're partnering with a small company called Diversa in Southern California that is going and prospecting for termites all over the world. And they bring them to the Joint Genome Institute. We sequence the bacteria, and we find out what these bacteria are doing. And termites are different in different parts of the world. Some of them are really good wood eaters that can put the ones you have in California to shame. And so then, so can you develop microbes that have the mechanisms of taking modest carrying charges and pass the rest of the energy on to us? Now, this idea of understanding the genomes and modifying the genomes of microorganisms is something that sounds a little strange, but it's a new area called synthetic biology. So fundamentally what this means is that you take not just one gene and put it into an organism that doesn't really belong to the organism, but you put in tens of genes and put it into an organism. One of the poster child of synthetic biology is a cure for malaria. Malaria kills about 1.5 million people in the world today, but the protozoa that causes malaria has become resistant to the standard quinine-based drugs. So there has been a new cure found called artemisinin. It can be extracted from a plant that grows in Asia, but it's small quantities. And so there is an artemisinin shortage worldwide now because, remember, many, many more people are dying from malaria because the quinine-based drugs are ineffective. And in fact, there's so much of a shortage, sadly, that countries, in particular China, have a great counterfeiting scam going on where they actually put in cornstarch or whatever to mask for the drug. The real danger is sometimes they put in trace amounts of the drug at a 5 or 10% level so that a very simple test can tell that there is some of the drug in there, and that's really bad because that will encourage the protozoa to morph into resistant protozoa. But anyway, this is a real serious problem. You want to drive the cost down. And so Jay Kiesling, Division Director of Physical Biosciences, a professor of chemical engineering and chemistry at Berkeley, has taught both E. coli and yeast to grow this drug precursor. That's Jay, just in case you want to know what he looks like. And this work got the eye of the Gates Foundation, and in January of 2005, they gave Jay and a startup company designed just to deliver this drug to third world countries was given $42 million to make it commercial. And so this was the milestone. How do you elucidate the pathway and cloning of the genes that will make the drug, the functional genes, and then productions at higher and higher levels? This is milligrams per liter, not grams. And the final one, the industrial goal was 25 grams of protein per liter. This arrow are the times where they've achieved the milestone, and they've actually just passed this one. So they're ahead of schedule to deliver the drug at 20 cents a cure to third world countries. And because it's molecular biology and yeast, you won't be limited. You can just crank up. Amyris, the company that was given the grant, they said, you got to deliver this drug at cost, but any IP and know-how along the way you can use for whatever else you want. That's the hook that gets top people into this. And already they've got first round funding because the drug is a multi-ring hydrocarbon that is closely related to a fuel. And so now there's a huge difference between fuel and a drug, but the way these guys are going, it's not, Jay says it's within an order of magnitude. Okay? So the idea here, but then you can talk about, so what am I talking about? Consider what yeast does. It takes simple sugars and it turns into ethanol until it gets to be about 14 or 15%, and the ethanol kills the yeast. So what you really want is you want a critter that creates not ethanol, and you can breed yeast that are alcohol resistant, but you really want something that creates. You start with butanol, which can be mixed at any ratio with gasoline, but actually a heavier, longer linear chain hydrocarbon that at a certain fraction, like 10 or 20%, automatically separates from water. So it's a continuous process. Okay, and so we think we can do this. Okay, not yeast. That's a 5,000-year-old technology, and ultimately, I have to say that alcohol should be drunk. So, although not in those quantities. Okay, so this is the University of California, Berkeley. For those of you who don't know, that's the famous stadium. There's a grove of oak trees where people are camped out, so never mind. And up here is Lawrence Berkeley National Lab. And so next to a new nanotechnology building that costs $87 million to make, and it has a $20 million budget, next to the National Center for Electron Microscopy, which will have within 3 years an electron microscope which has enough spherical aberration correction so you can have genuine atomic resolution, not rows of atoms, but genuine half angstrom resolution, where you sit at the focal plane. So instead of getting a computer reconstruction of different misfocuses that you get out the spherical aberration, you can sit at the focal plane, which means you can take movies of nanoparticles and crystals growing and defects moving. At atom by atom scale, and by tilting your sample, you get atom tomography. So we have that facility. We have arguably the most productive synchrotron facility in the world, certainly in the soft X-ray, but also in protein crystallography, even though it wasn't designed for that. We have molecular material science building. So we want to stick a $160 million building there where the plant biology guys, the molecular biologists, the solar guys, photovoltaic guys, and everybody else could be in this building. So that's going to be the site over here. So how's fundraising coming? Well, we have a good start. So we raised $500 million from BP over a 10-year period. We got $70 million from the state of California for the building. The University of California has agreed to use general revenue bonds, so we can get tax-exempt bonds at 5.5% to get $60 million. We've so far raised, it's a little more than this, but a scale 15 million from private donors, and already 4 million to start the research in this year, 2007, because we're waiting for the federal stuff to come in. There's one renewable energy chair. There's actually, I just found another chair. And we're going to be applying for a $125 million over 5-year grant from the Department of Energy for the bio part, and we hope that this is a start. We're not going to get the 15 million because that happens to be all the money the Department of Energy wants to spend on material science for fiscal 08, but we're hoping to get half or a third of it, but we're worth it. But we've applied for all of it. But hopefully, and this mood is rapidly swinging in the country, that this type of money will ratchet up to, quite frankly, it should be about $1 billion a year in energy research in the United States. And then we're talking with private foundations, and we're actually trying to get industrial partners, not only for the money, but this is very different because it's not academic research. Academic research, what do? You write a bunch of papers, and you make sure that those bunch of papers will get you funding for the next cycle of 3 or 5 years. And then after you write the papers, you go on to the next thing, because what you're really trying to do is to become famous. This is different. You're trying to solve a problem. But it's a problem of industrial strength. And in order to solve this problem, you need much more than just getting personal fame. And the scaling is going to be a couple orders of magnitude. And that makes it very different. So we need industrial partners at the get-go. The Los Alamos is a multi-scale operation that got very bright young people. This is one person that was put in charge of a theory section when he was in his mid-20s. That's Richard Feynman. So sitting amongst Enrico Fermi and Oppenheimer and others. So there's also the need to identify young talent and give them resources early, not to wait until they're 40 or 50 or 60, especially 50 or 60. This is a place where I worked for 9 years that also had a knack for giving young talent resources. And in the invention, for example, of the transistor, this is the first transistor. You think of these guys who got the Nobel Prize for the invention of the transistor, but in actual fact, there had to be fundamental breakthroughs in material science, in theoretical physics and experimental physics, and a basic understanding of many, many things that required a bunch of groups working and communicating with each other. So it only took 9 years from the discovery that two semiconductors can act as a diode, and they said, we think we can make a transistor, to the announcement of the transistor. And then the following 10 years or so, much of the foundations of the semiconductor world were laid at Bell Laboratories. This does not happen in academia on that time scale. So the idea here is that we would like to gather up the talent and the structure to do this. And I just wanted, this also is in the DNA of Lawrence Berkeley Lab. This last year's Nobel Prize was given to George Smoot and John Mather. Mather was a graduate student at Berkeley Lab in Berkeley. George Smoot entered as a postdoc. He became in charge of the project that led to his Nobel Prize when he was 32. Another great discovery that the universe is not only expanding, but it's accelerating as it expands. This is a $1 million prize. This is another international prize. These are precursors to this one. And he started a group that ultimately captured several members in the National Academy of Sciences, but he was the leader of the group in his early middle 30s. So this is what we're trying to do. We're trying to capture what happened at Los Alamos, what happened at Bell Labs, what happened in high energy physics, and is still happening today at Berkeley Lab, but to transfer over that to material science and biology, which is much more individual based. And so if we can do that, then we've got something. And if we can get the money, that's what you need. You need the raw talent. You need an organizational structure that allows individual genius to assemble a team, and for management to give them the resources they can go fly and not write a proposal. That takes too long. And Bell Labs, we didn't write proposals. We went to an office and said, I got an idea. And we talked about the idea then and there. And so this is another issue. So, if this happens, we would like something that keeps the climate here the way it is and keeps the lights on. So with that, thank you. I'll take questions.
How do you keep the federal government focused on energy as prices oscillate quite a large amount?
It's climate. Climate change is very different. In the mid 80s, when the price went down to $20 a barrel, all the new technologies that were being developed just went out of existence. This is different. If you the final cost of the climate change, you pick your favorite, whether it's no water to drink or irrigate your crops, or huge millions of people being displaced from areas like Bangladesh or Florida or Louisiana, or just go down the list of things. There are going to be huge economic costs. By the way, and it hasn't escaped people's attention, that even for the remaining conventional oil, there's there's all sorts of people positioning to have access to conventional oil. And that shapes a lot of the foreign policy. I gave a talk at a meeting of finance ministers in China about a year ago, tax and fiscal policy regarding energy, and I said, well, I think it's no secret that China is modernizing its army so it can guarantee access to energy, and everybody went like this. Right? It's not that you're going to invade, it's just the presence. It's like part of the reason why we have a Navy. That's a part of the cost. And so regardless of what you think of the current temporary situation, in the long term, getting access to energy and natural gas and oil are increasingly defining points in the geopolitical world. These are all costs.
I have a oil question and a high energy physics question. The oil question is, what are the relative energy costs of cracking oil into kerosene versus gasoline?
I don't know.
Okay. And the other one is, have you had a chance to evaluate Bussard's fusion work?
Partly. And I was discussing it with people at Google for, I don't know, an hour and a half, and it's continuing. And let me just say, so far there's not enough information so I can give an evaluation of the probability it might work or not. But I'm trying to get more information. I've talked to them a little bit. Yeah?
A couple examples of some solar kinds of energy that can be produced. You said that we would need a 50th of a percent of the sun's power, something like that, to produce our current energy.
Yeah, 0.04.
Yeah. Isn't that going to raise the temperature, lower the temperature of the Earth?
Why would that? You take it.
Some of it would have.
Yeah, you absorb it, you reroute it, and you release the energy, and some. So I think it's net balance. I don't know. Reflectors to generate electricity from heat.
Right. Tower that does what I described.
There's actually several things, because variants of this. There are parabolic trough reflectors that take, the little. Oh, okay.
Yeah. Is releasing hot air at the height of the chimney likely to have global warming impact?
Okay, just off the top of my head, I'm saying that it's a net, there's a net input of energy from the sun. And then what happens is there's a radiation of the heat. So we're in quasi-equilibrium. You absorb energy, you re-radiate to space, and in the form of infrared radiation. That's why this greenhouse gas stuff, right? It reflects the heat, and so you get a little warmer here. And so anything that generates heat is more or less going to be the same. You're going to get some radiation through the water vapor, through any greenhouse effect, and it gets re-radiated. So that stuff is just, on the gross scale, it doesn't really change anything. Okay.
Back to biofuels. We've been hearing for a while about how not great corn is and how potentially great wheatgrass or switchgrass and these other materials could be. Is there a funding shift, a policy shift that's going along with this? Is that not happening yet? I mean, I know there's a lot of invested interest in the agricultural industry to keep things in corn, and certain states are interested in that.
Actually, no. I would say the farmers will switch very rapidly. Every year they make a decision, and what drives the farmers is so it's not that. It's really the cost. Right now, the farmers don't have a market if they went to switchgrass or miscanthus, because there aren't it's not industrial strength, commercially viable mechanism for getting cellulose into ethanol. So that's why I talk about this factor of 2.5. There are pilot plants going up. There are new technologies that there are going to be a few pilot plants invested in the next 3 or 4 years of improved technology to break the cellulose down. Once you've got that going, these pilot plants that can take the cellulose, then the farmers, it's one season. They would actually prefer growing weeds. Why? Because you don't have to till the soil for 10 or 15 years. That means the huge capital investment in in diesel fuel, in fertilizer, it's 1/10 to no fertilizer. Irrigation costs go down. So the capital investments go way down for the farmer. And so even if they get the same return, or 80% of the return on their crop, they don't have to bet the farm or half the farm every year to put in these huge capital investments. They would love to do this. Also, by the way, the agriculture in the United States is not sustaining now. The water table's going down in the Midwest as more farmers begin to use irrigation. The nitrate runoffs are huge. There's 1/100th the soil erosion of a grass, a C4 grass like miscanthus or switchgrass than corn. There's all sorts of reasons why you never want to use corn in the long run or even the mid run for growing energy.
It seems that there's a lot of state politicians and a lot of certain organizations that are still pushing money towards the corn ethanol solution. And I guess I'm wondering why. I mean, why is that not shifting towards other
I would guess, yeah, people like Archer Daniels Midlands are doing that, but I've started to talk to the farmers. They're, you know, and they feel very differently. I think it's more, right now there's a technology that has a market, and so as soon as you establish a technology, biorefineries that where they have a market, they will start switching very rapidly. And look, the U.S. government knows this. At USDA, DOE, and the president actually knows that this is just a transition you want to immediately switch as quickly as you can. You know, there's not that much difference in CO2 emission from burning gasoline as there are from producing corn, but there could be a factor of 10 from cellulose. So you know, there's huge gain. And the productivity, oh yeah, productivity per acre. Corn is 250 to maybe 350 gallons per acre of ethanol per growing season. And miscanthus at 20 dry tons per acre, not the 26 in that field you saw, will give 2,000 gallons per acre. The yields are higher, the soil erosion is less, everything's better. It's just get better enzymes, get better pretreatment. Design the plant so it's easier to break down. We can genetically alter the ratio of lignans so you recover twice as much sugar. We already know this. We now are thinking of trying to alter the lignin so there are attack points so that we can design microbes to break down the lignin and separate. The lignin actually is a very high fuel hydrocarbon that you can think of syngas type stuff or using it to burn to power a biorefinery. It's, you know, actually, you know exactly, this is why it's so exciting. You know exactly in the next 3 or 5 years, in the next 10 years, where you want to go that you have a reasonably good probability that you can transform the whole process. That's why BP and DuPont and others are investing that kind of money. It's not a, you know, wild, woolly dream. Any other? Okay. All right. Thank you.